Have you started on Honey? I'm about to.
Oh, you haven't done that?
I saved it for last. Because then you can check the output.
No, yeah. I think it's easier to do JSON, right? I don't know.
It's actually not too bad. It's only like a couple lines more.
A couple lines.
No, it's D3.NAS. It does like all the work.
No, there's a lot of
Entries and keys, yeah.
no, entries and keys, but it's objects of objects collections.
Is it that bad?
No, you have to think.
Have you done the other parts?
Do one part of it.
What did you think of the previous homework?
Something like that, like no, but I get to do non-based like JavaScript. Can you use I will yeah, I can do this.
Yeah.
The next one. Is this one you want? Huh?
A few more homework. Put in this one and then.
Ooh.
Okay.
How's your career? It doesn't. It's still a long time.
Hey everyone, welcome back. Today we'll have Ilkin Safarli, who is one of your teaching mentees, teach the lecture on layouts. Layouts are super important for anything that is not like a standard bar chart or a scatter plot. You need some kind of layout. Before Ilkin gets started, on Thursday we will be doing a little bit of like talk a little bit about what the exam is going to be like. I'll give you some kind of guidelines on like how to critique a visualization. There's going to be critiquing on the exam. There's also going to be, since we covered a lot of coding stuff, there's also going to be coding questions, but I'll go through all of this on Thursday. Administratively, I think you have quite a while until your next homework is due, so I assume there's no questions yet. Remember, there's a lab tomorrow, the usual place and time to introduce homework 5. Anything else that you guys want to bring up? Great, so Ilkin, please take it away.
Thanks. Good afternoon, everyone. So, first thing, my voice is usually not loud. People in the back, can usually come forward. Or if you still can't hear me, you can just raise your hand and let me know. Okay, so, and what I'm asking is, I have moved my office out tomorrow, so I will announce the date later on slide, so you can just check that. Okay, so today we'll be talking about layouts. So, what's a layout? Anyone? Layout and visualization. What do you mean by layout?
True.
Go ahead.
It's a way of organizing the data so that like things are in.
Yeah, exactly. Organizing or positioning like the elements, not as the SVG elements that we have. Yeah, I mean, it might be it might be more, it might be like a line chart or something. So we already have seen simple examples of layouts in our homework, which are mostly driven by data. For example, we have like, remember we have the scatter plot, and we position the circles and the lines based on our data. So this itself is a kind of a simple form of layout. Or we also have done a tree layout. If you remember the homework, circles on the tree as or 2. So we had to basically create a layout for a tree, and then we basically wrote an algorithm that creates the layout of the tree, and then we render the data on the screen. So, and there actually, I mean, these are kind of really simple forms of layouts, but they get much more complicated, and then sometimes they're like a deterministic algorithm to give them like the exact positioning, especially when we come to the not like the graphs or like no things that we'll talk about later. So, but they are like that simple always. So I will start. Basically, I will basically look at some busy examples of layouts, and I'll mostly go over the code and explain what it does. And then at the end, we'll also talk about another library, which is really cool thing to have layout. So first thing is, we'll start with pie charts or donut charts. I know Alex doesn't like them much, but like if we don't have like much categories and like a single data, they're kind of useful. So in D3 basically we first gotta create a pie generator, D3.py, and you can give your data, you initialize it or not, you can also specify later. And then we will, but the pie, D3.py doesn't give you it doesn't know anything, it just gives you like the data, the necessary data of the position yourself. So it basically will return you the start angles and then the end angles, and then that's basically the most important things that we're going to have the start and end angles so that we can arrange our data from the circle and then divide it into sections. So here we will go over an example in the code. So by the way, can you see everything screen? So zoom in or? So we have our data, simple data, which is based on like the OSs, mobile OS, the Android, iOS. Yeah, well, I think we have like 4 categories. And then first define our width right there, and then we give it the radius of our circle. And then basically this stuff, we append our SVG, define the attributes, width, height, then append the G, and then we translate it. And then we define a color scale just based on categories. So we have here, we have 5 categories, so just give them 5 different colors. And then here we kind of like the, so far you have seen all of it, and it's like important thing that we did the pie generator here, just saying it's with a pie. You can leave your data right now if you want, or you can also assign it on. So we also want to say which value it should use, right? Here we have like the categories, like OS itself and the share. So the value you're gonna use here is the share, right? The market share of a given OS. So we just will give a simple function that says, okay, so d.share should be our value. So this is gonna use it as the value, and when it creates the arcs. So here, basically have said pi data. We just give the data right now. We'll define the layout and we just give data. We actually print in the console. I will. It actually open the console. So you remember I said that in the beginning said that it should give us the start angle and the end angle. This is the most important thing for us. So here when I print out in the console, I should be able to see the start and the angle. So I'm just going to open up a console and so here we just going to take a simple look at one of them. So just see the Android, you will see the, we have the data bits attached here, and then end angle, start angle, and the index. So these are basically like the, since like the first one, it kind of like start from 0 and then, okay. I think the angle is probably, so then we'll use this data, and then we'll use data arcs, which will actually create the path element itself. And after that, we'll append the path to our SVG, and then we'll be able to draw the pie chart. So basically, the data arc is what is going to create the path element itself, and the data format produced by the dt.py is essentially we'll just provide it, and it should return us the path. So, and then like certain options that we can define. One of them is outer radius, and the other one is inner radius. So we're going to change this and see what the effects later on. And then we also, here we basically arc pi data 0, and then we'll give it the first data, and then it should give us like the path. And I'll show the open the console, and we should be able to see the path in there. So it's like the first arc, and then so it's basically an SVG path element, and if we append it to the SVG, we should be able to see it on the screen hopefully. And then basically just give the pi data that we created, and then append some group like G elements, group elements. And then just path, and then we append the text, and then you should be able to see the result here. So this is basically our pie chart now. So, and okay, let's say you remember we had up there we had we can say things like the Android dominates most of it, and probably don't have the Windows anymore, but yet still there. So you remember we had there like two radiuses, like we had columns inner radius and outer radius. So what's will happen if I, let's say, change this one? What do you guys expect to happen? Yeah, let's see. So here I don't change like much simple as that, like for this you just change the file and then you have a donut chart. So it's a real simple example. I mean, sure you can do it yourself, right? You can write the code to generate a pie chart or a donut chart yourself, but I mean, in this case it might be easier, but later on other layouts actually gets much more complicated. So since all the implemented, you might use this one. Yeah, I think we have just a screenshot of what I just showed in the console, and then here's like transformation again. So yeah, it was basically for like simple case of a layout, and then any questions so far? Yeah.
When you create the pi data, is that assuming percentages, or does it normalize that?
I think so. What we have is adds up to 100. It's probably kind of normalize itself rather than just taking basically. You can check the documentation to make sure, but I assume it just kind of takes the ratio and calculates it itself, so it doesn't have to be add up to 100. Actually, we can change the thing and then see what happens, right? It's making those. It looks like it does, so yeah, it doesn't have to like add up to 100, so it should. So you can just, by the way, go ahead and just play with the parameters and see what affects your visualization. So it looks like it doesn't have to add up to 100%, so it can like any value. Any other question? Yeah.
Where do the labels come from?
We append text here somewhere, and data.os. So see now data will set OS here, right? Then at the end we append text is here and then here. This line. Okay, so any other questions? Okay. So now we'll talk about hierarchical layouts. So these are kind of like more interesting than the pie charts. So you remember in our homework track, we had an example of hierarchical layout, right? We had the tree, and it's essentially a hierarchical layout, and basically we have like this. The first level you have the root node, and then second level you have children of root, and then third level you have like the children of those children, and goes and so forth. So it's a hierarchical layout, and there's like kind of a hierarchy, like from like the upper level they go down. Yeah, so first we'll talk about code layout, which might not be actually a good example of hierarchical layouts, but yeah. So they're essentially kind of good way for visualizing visualizing flows in a network, or kind of a big flows in a network. What I mean is that you might have edges in a given network, a graph and other links. And if you say that, say you have the values, so like edge weight, so let's say all kind of number of edges, you might have, let's say, 10 nodes, and like in between you might have 1,000, or in this case, thousands of edges. So if you try to draw it with a kind of a node link diagram, you're just gonna get a mess because you have only like 4 nodes in our case, and then you'll have thousands of edges, and it will not look good. So it's kind of like a good way to visualize the flow of a given network. So here we have a simple network diagram which we represent adjacent matrices, which essentially means that, if you're not familiar with it, so we have kind of like 4 nodes here. You can assume that node A, B, C, D. And then the first element represents the number of links between from A to A itself. And this one is from A to B, and this one is from A to C, and so on. So it's kind of a simple way of representing a graph, a node-link graph in adjacent matrices. So here we have our simple graph, and then we'll try to apply a code layout and draw a code layout of this network. So there are 2 functions that we're going to use. One is the core that produces our layout, and then arcs that is basically going to generate a path to basically generate a path so that we can draw them, and then the ribbon that would generate like inside what we actually have like inside the links. So I'll show the diagram and then it will be actually much clearer. And then we obviously need the source and the target, so it's kind of like, I mean, in this case, or for example, I mean, these are kind of all assume that kind of edges, and then, for example, for this one, like the second one here, and say the source is A, and the target is B. It's kind of like node diagram, source target. So, and then we obviously need these to kind of know that from which node to which node we should draw the path. And then again, since it's kind of like have a similar structure, so this one is the arc, right? We also need a data that has like the start angles and then the end angles, and then obviously the value and indexes. So I'll again go over the code, and then so we have our data defined here, and then we have the basic SVG stuff that we append them, and then define some of our variables. And then we have a color map here that define a categorical color. And then here basically we kind of, this is the code generator that we say we do that code, and then we only set the pad angle. I think it's the angle basically. I'll change this one and see what affects the actual thing. And then we have the arc, as you see in our pie charts here. We again define inner radius, outer radius, and then we have the ribbons that we also give the inner radius, and I'll show what happens if we change all of them. And then we kind of console log it, and let's see what it looks like. Things file this. So again, you can see like we have basically the end angle, start angle, which is kind of the most important thing for us, and then we kind of format and ignore the rest of it. So again, this all gives us like the layout of positioning. It doesn't render anything on the screen, so we have to do it ourselves. So again, we'll create a group and then add the group. So we'll have basically 4 groups. Since we have like 4 nodes, and then we'll append the paths, and then kind of color them, and then the arc will define the paths, and then append the ribbons up, and then it just kind of append the path, and then do the path itself. Okay, so essentially, then we kind of like do some random transformation and then add some text. But so here what we have so far is basically at the end you will have this one. So it's kind of, you can see we have like 4 nodes and we have 4 groups here, and then these are kind of our groups, like the 4 groups, and then these are basically represent basically the link. So kind of basically the flow from, let's say, this node to itself, or from this node to this node. So I'll actually show an example which is kind of based on migration data, and it makes much more sense. And then so this basically the outer circle. See, it's kind of a donut chart, right? We saw before. The outer ring is kind of a donut chart, and we kind of created with the arc, and then let's say we kind of, I'm just gonna modify some parameters. So this is ribbon, let's say, I'm just gonna say O2. And this is kind of like, it's kind of 2 separate things that we draw, and one is basically the circle outside of the link. That's kind of a pie chart, and the second one is the ribbons that kind of represent the links themselves. So it's basically a good way to represent the flow, and if you have lots of like edges, or you have to build high weighted edges, and then you have you have like a limited number of nodes. Would it like kind of work if they had, let's say, hundreds of nodes like this layout? Would it work like good? What do you guys think? If you had, let's say, here we only have 4 nodes, like 4 categories. Let's say if you had like hundreds of nodes, would it be a good way to visualize it? Why? Too messy. Yeah, since it's like a circle, and then, sure, you can make it look big, and then like you have enough space for each of them, but then it will look fit on screen, right? So, if you have like a limited number of nodes, and then you can visualize it clearly, but I will say even like more than 10 or like 20 will work. So, I think I have a good example here. It's kind of like, so this is kind of example of this line, number of people migrating from one country to another. It's kind of based on like regions or something. So here you can see this kind of makes much more sense, right? If you, let's say, look at the Soviet Union, and you see that actually, they just move inside the Soviet Union, right? They're like tiny amount moving Europe, but that's it. And most of it's kind of like staying inside Soviet Union, and not moving anywhere else. Or Africa, it's kind of applies the same thing. You have like the migration inside the Africa itself, but I mean, there are like all like one outgoing link that goes to Europe. Yeah, and then but there's a kind of actually like South Asia. There are like also people moving south from South Asia to West Asia. You can see, but it's like kind of what can you say that from what will be your conclusion by just looking at this migration diagram? Let's say you're analyzing the pattern, and what will be conclusion like from this diagram?
A lot of people are migrating from Africa to Europe.
Is it a lot?
Well, that's where most of the people are migrating from.
Yeah, you can say most of the people migrating from Africa, yeah, going to Europe. But I will actually say that it's like mostly the migration is kind of mostly like inside the regions rather than outgoing. Like rather than switching it to a different region, they usually stay inside like the same region, right? I mean, if you're Soviet Union, almost everyone stays in there. I mean, Africa is like almost everyone stays in Africa to the Caribbean, or let's say in East Asia. It's kind of like yeah. I know you can also or you can also analyze like a different individual regions themselves. It's kind of actually an example that makes much more sense other than our like made up example. So, any questions so far? Okay, so now let's move on to tree layout. So we had a simple tree layout example, right? You guys remember? So it was actually like tree layouts are kind of like real simple because you know that there won't be like any links coming back or like I don't know. I mean, since like all of the elements inside the tree will have only one parent and might have a couple of children, it's gonna be really easy to lay out because you will start from the top level hierarchy and then move to the next one and move to the next one, and then you can simply basically in a let's say in a logic diagram you can just do as simple as what we did in our homework 2, right? Maybe you can modify a little bit just so that like the root stays in the middle, but you can just do a simple thing. But it turns out that you don't have to do it by hand as we did in our homework. Sure, I mean it's a good way to write and practice it, but there's also all the implemented tree layout in the D3 which you can utilize. And so here we have a simple data. Just get so we have basically the root node just even, and then we have kind of children of it and then the children of it. So it's kind of like goes like this. So you can see the data is already in a hierarchy format. So we have like this node, and then we have children of it, and then we have like then we have like children of this node, and then for example we have the other node, and then we have the children of them. So it's kind of in a nested format. It's already in nested format. So we can basically just take that and then use it. So here we'll first find the root of it. So if you since it's in hierarchy format, just say you did the hierarchy and then get the data and the children. So it will basically go in the root. So okay, sure. So this is a kind of example of hierarchical data, but what we do is actually we provide it in SVG, CSV format, and then it will return us the hierarchy format. So what we provide and let then get. I'll show it goes along. So basically, it's basically they're basically predefined the three functions that can format the data for you, so that it will be in all the three formats, so that you can take it and then draw it on the screen. So here, for example, so here we have this data format here, right? We have like name parent and the name parent, but it's not in a hierarchical format, so it isn't like something like this. So where we have like the root node, then the children, and then children of those. So if we give the CSV format to D3 that specify and then tell that okay, this will be our ID. The node IDs are represented by the name in the data, and then the parent key represents the parent. So basically, we have to tell it what is the node or node ID and the parent ID, and then it will give us the data and the root of the tree. And then once we have the root, then we can give it to the tree layout, and then it will give us the positions, and then we can take them and then put them on the screen. So this is the root node that in the console log. So you can see we have the children of it, and then the data, and then IDs, and then this is the root node. We don't have like the parent and the parent. So, but you can see here that we have the children and the node, and then we have the ID of the children, and then we have the parent represented as a node object. So, I mean, we obviously have the data field, and then, but like the most important fields are the children and parent for tree, and then we also have the height and other stuff. And we can also, given a node, given a node object that is returned by the set for hierarchy, we can use we have only two functions that node.ancestor, and so it basically returns you like the parent of the node, and then descendants returns you like the children of the node. So all the nodes the specific node and include the node itself. So let's say, I'll show you an example. So let's just go over the code quickly. So we have the data here, like top level, and then we have children of it, and then we have children of those. So we have basically two levels, and then we define our parameters here, and then define SVG height, width, and then margins, translation to somewhere, and then we also probably have some kind of animation. And then basically what the collapse will do, it will basically, you have it will just remove, let's say if you have a node and then at some level and then you're interested on the children of it, so it just will remove it. So what the collapse do is, it will take the children parameter. You remember we have the children in the right, an object. If you just make the children null and then store it in some other value that the DT doesn't know about, but they actually know that's there, so you can restore it. See, if you just say DT underscore children equals to this. Yeah, these are children, and then we call like casually, and then we basically say children is null. Since we don't want the DT know about the children, so it doesn't show us anymore. So here we kind of find the nodes links, and then I'm just gonna quickly go to the layout itself, and then so this is basically what we get when we kind of like draw it itself, and this kind of be really useful in your homework 5. We almost have the same thing, or like the same structure, so we can just use the code from here. So and if you remember, we kind of collapsed it. We actually called it collapse, so it doesn't show like the children nodes here, but so we also have an event defined there. So when you click on it, it will bring them back. When you click back and you call the collapse, and you'll kind of remove them. So here's our events defined there. We kind of like to create the current path. We just tell it how to basically create the path itself. So it kind of like takes the parameters, source and destination, and then and then we do some transition here for the node for the like collapse on collapsing. If you so we just click this kind of animate there. Okay, so here we basically define the layout itself, say tree map, is actually not tree map, but yeah, we kind of like give it the height and the width of the space that we want it to be like a rectangular form. And then so we kind of just define the layout here and then we just give it, we have the root here, just by the hierarchy. And then we basically will call, we just call this one tree layout. Remember the tree map is the layout, and then we give the root and it should return us the positions. So and the positions are defined in and yeah, so we have like positions defined the like I think x, y, and 0, y. So yeah, and then we once we give the tree the root, and it will return us an object that has the x and y coordinates, and then we can basically take it and plot it. It's kind of like similar to what we did like with the level positions in our homework, but you just give it the x, y position, and you can take them. So you can go over the code and modify it and see how it changes also. And it's kind of a little bit like helping your homework. It's like almost the same thing. You know, homework 5, the tree structure, and you can basically use the code from here if you like. So I will know tree map. So what's a tree map? Does anyone know what's a tree map? So I have a graphic here that kind of shows what a tree map is. And so let's say we have this is like the most intuitive way that we visualize tree, right? We have the root node here, and then we have children node here, and then we have the children node, right? And then the tree map is kind of a way to visualize the tree in a kind of different form. But what makes it easy, it's kind of makes it easy to spot like kind of clusters. In the end, kind of like if you have an attribute or something, it's kind of like a good way to visualize the attribute as well as an area or like its height of this rectangle. So here you can see like we have the A, C, and then the whole rectangle itself is the A, like the root of the tree, and then we have C, we have like B and C, the children of it, and then it's kind of like divided into two. We have B and C there, like the rectangles there, and then further we divide B into like B and E, we have here and here, and then C has 3 children, and we have the children here. So I mean, it's like kind of like not intuitive. You look at it, try to understand it, but let's kind of like put them side by side, and it's kind of easy to understand it. So here we have. So we have a sample data that is kind of the D3 like library, so kind of I would say the part of the D3, like the part of the libraries are kind of part of the D3 source code, and then their sizes. So what you have is size and then the path. So the path is can think about the path in a file, like file path. So how is that tree? Okay, so it's like you can think of the D3 as the root of it, and then you have D3 array is kind of like children of it, child of it, and then the D3 array has these like other children. So it's kind of like separated by the slice. So you can think that like each slice is kind of a level of the tree. So it's our tree format, and first what we need to do is we basically need to get in a format that you understand this. And then we'll use the tree map. Like instead of t.tree, we'll just say the tree map. And then the so since here we are kind of drawing a rectangle, right? Instead of just positioning a circle or no, since we are drawing a rectangle, you remember we have like at the end it should be something like this, right? Something like this. It's kind of represented by rectangles. These represented by rectangles. So we need like the 4 coordinates like x. So at this point we need like these 2 points, the coordinate points to those rectangles. So the value returned by the tree map is gonna have like x0, y0, and xy, and then y1, and then we can use them to draw our rectangles. So I will quickly go over the code example, but if you want, you can gonna look at it in more detail to understand it. So again, we have like the simple stuff defined here: SVG, height, width, color, format, gonna format size, and then yeah, actually, I'm not sure if I just so we are loading it from pp.csv. It's essentially the file format here, but it's a much bigger file. So you load it, and then we need to first find the root and get it in the appropriate format. So we use this as a set file, and then we say, okay, ID is gonna, the path is gonna be the ID, because they're gonna be unified to represent them, and the parent ID. Remember, I said we kind of each slash represents the hierarchy in the tree, so we kind of basically find like the parent of it based on slash, and then we need to so we also need to find like the data for the parents, right? We have the children, but the data only shows us the sizes of the children, like the individual libraries, but we also have to find the size of like this parent. So we also sum it up here somewhere, and then also sort it. So and then we say tree map as we just said for like with the tree is almost the same thing. And if you say tree map, it's gonna always actually modify our root node, so you don't have like this equals something. And then we'll give it the layers. So it doesn't like actually include the root itself in the picture. So and then also here what we do is we basically give like the GitHub URL. Since if you just click on the node, it actually take you to GitHub page. You just assign it's like not necessarily just kind of assign the URL to the text so that they click on it in the map. It will take you to the GitHub page of it. So I'll show it. But it's like not necessary. Here we do like the most important stuff. So we just since different rectangles, as I said, mentioned before, we have the coordinates like x0, x1, y0, y1, which you can easily calculate the bit height. And then we'll append some text and then clip it to, then again append some text. Then at the end we should have it there. So here we also so you guys have an idea about what the colors represent? Actually, yeah. So if you look at the code, the colors are assigned. So we assign a color here. So you go like the 2 level up in the tree. So the colors that the nodes that represent the same color, become the same color, is kind of like have the same pattern. It's gonna have the same pattern. So I'll show it in the tree. So it's kind of like remember I said like it's kind of a good way to represent the groups also in the tree. So these will come handy if you kind of color them beautifully, and then you gotta remember. Can you guys see like the URL down there? So like see it's like kind of tt.geo and then extend. It's also part of tt.geo. So that's right. So yeah, this both library kind of extend, and then circle kind of part of tt.geo. So it's kind of, that's why they're kind of like colored in the same color. It's just the way that we color it so that we can then kind of identify the groups. So here we have our T3 map element. So yeah, I think that's it. Now comes the like the most like the part that I like to like. So the network layouts. What's a network? Network is, I mean, obviously the tree is a graph of network too, but by network to me is a graph. You can also have like loops or like kind of circles that you can like. There's no hierarchy. I mean, you can basically have any kind of nodes and edges in any combination. So I mean, it's easy if you have a tree or let's say a pie chart, and it's much easier to do layout, right? You can just implement yourself. But what about a network? Like, how do you lay out a given network? Any ideas? So by network, I mean, by network, I mean you can have, think of a network. So, I'll show what I mean by. Okay, so this is a network, right? We have main like nodes, edges, and they connected to each other with the nodes and links. So how would you do the layout of this? Imagine when I give you the initial thing, everything is on top of each other, and then I want you to do layout of this graph. How would you do it? Any ideas? I know it's not like something like simple, but I'm just curious if you guys have any ideas. Yeah? Yeah, go ahead.
You could like make the links and the nodes kind of like physically push each other.
Okay, yeah, that's kind of quite good. It's actually one of like earliest like like layouts that people come up a base to do the layout of a network. So it's kind of actually like most of the not most but like mainly they're kind of based on physical simulations. So what I mean by physical simulation is you can think of like the nodes themselves as positively charged or kind of like this charge in a, well, if I have like electrons as well, like, but you should have the same charge that they repel each other, and but we also at the same time we represent the links between them as springs. So you try. I mean, you can imagine that we have the springs. They kind of like try to pull them together, but we also have the repulsion that the circuits or the nodes like kind of try to basically push everything away from each other, and then and they push away, and we have the links that pull inside. So and just keep running it. Okay, so let's say I did this once, and then do I get a good result? What do you guys think? Let's say I just did one iteration, calculate and then stop. Do I get a good result? What do you guys think? So I did like calculate them once and then stop. Do you guys think do I get like something reasonable? I mean probably not, because I mean just I don't know, I think there's a tool that could actually another example. Oh yeah, cool sure. But yeah, it will. I mean just doing it once will not give you a good result, and you can kind of like actually the things like in layout, what we usually do is. So there are like two ways to stop. One is basically is Weyrich equilibrium. I mean there are like multiple ways to define it, but the easiest thing is you can take the difference, the position difference. Let's say you do the layout and then record the position of the nodes and do one more iteration, and then you take the difference of positions from the previous layout, previous iteration, and see if it doesn't change much, and there's usually sigma that's defined or delta defined by the user. So if it doesn't change much, then you say, okay, it must be good, then I can stop. And then sometimes it doesn't reach equilibrium at this with this delta, but then you have to like give it a maximum number of iterations. So what I mean is you have a basic condition saying if I reach the maximum number of iterations, or I reach the equilibrium position. So whichever of them happens first, you're gonna stop, because I mean you don't want to run forever. If you run it, forever. So you have have a stopping criteria. Yeah, and I think that the layouts are usually I would say thousands of iterations. So but the idea is kind of usually just give user to define it. But yeah, I think. From my previous experience, we will have 1,000, between 2,000 iterations. So, yeah, the thing is, when it comes to criteria, okay, let's see, I did my layout, and then I have something on here, and the position them, nodes and circles, and then how do I tell if it's a good layout? What's a criteria to say? Okay, let's say I have this one here, this layout. Let me find something that is static. or this one, I'll just show some instead. Is the good layout? That's not. Okay, so, yeah, so think about like this. We are done with it, and then so is the good layout? What do you guys think? I mean, what should our criteria? Yeah, yes. Come on, guys. Okay, one thing, it should look good. It should be good. This is one thing, but there are also like quantitative ways to analyze it. I mean, you can take the simplest thing, link crossings, or not to not overlap, or the total area. I mean, you can make it really large, right? But it will not have like not overlaps, but it's kind of like way too high, way too large, and for like a screen. And then or you have like the average edge length. So there's like different kind of quantitative methods that you can use to analyze your layout once you are done with it. So now we'll take a look at how the layout and the link diagram in DT first, and then we'll look cytoscape.js later on. So, okay. So yeah. So here we have, I think it's from, yeah, so we have, I mean, it's like the format that your data should be to get in the DT. It's kind of like just say nodes and then links and then give them IDs. And then kind of like in the links or edges, you just say source and targets. We have like obviously different source and target so that I know from where to like I should throw it. So it's the data format that your data should be in, should be formatted accordingly. And then forces. So they're like, as I just mentioned, we have like, it's mostly based on force simulation. So there are like a couple of forces that act on a given layout in DT. So, and there are like a couple of them like links or like things that kind of pull them together. And then we have, I think, many was, I think it was, I think we actually had an example before. I think it was like one that force each other. I think the centering is basically tries to keep the graph in the center so it doesn't like fly away somewhere, and then the collision is basically so actually so they're like it's actually easy if you have a nodes and then you don't consider the size of the nodes and then consider them as a single dots. It's actually much easier to do the layout because you don't have to basically worry about collisions much because just take every single dot in a space and it's much easier. But if you have shapes, or let's say not uniform shape, nodes and something like it's more like bigger, so it's actually much harder to do the layout since you have like consider the collisions and calculate them and make sure that they actually don't collide or overlap with each other that much. And then also have the positioning, which I think in the tree just puts in a specific position, I believe. So yeah, this is how you initialize simulation. You say the t.post simulation and keeps you a simulation, but so as such the way you initialize it, and then you'll basically have also use these three forces that we have the links and charge and the center. The links is, remember, it's one that pulls them together, and the charge is the one that like the same charge like electrons getting electrons and push them apart. And you also have the center that's gonna try to keep the whole diagram in the center so that it doesn't play out for you. So and we'll also show like what happens if you remove all of the like each of the forces and then say so if you run it you will get something like this or this data set. But yeah, here we have the force link, you remember? It was the one that keeps them together, right? So and what do you guys expect is gonna happen? Did you guys show the picture? I don't know. What do you guys expect to happen? if you remove the force link, what's gonna happen? Yeah, it's gonna be real nice for you, but yeah, it looks really nice. It looks really nice, but the thing is, we lost links and you cannot make any sense of it. Maybe I mean it's like a I'll say fibers or something. I don't know. It's like yeah. But things like here, actually here, when you have them, you can actually see the clusters, right? This kind of clusters, how they can kind of identify the clusters, but once you remove it, it just doesn't make much sense. But it looks nice. So, okay, next we'll remove force many. So what was the force many? It's the charge that kind of repels them from each other. What's going to happen if I remove it?
Come together in the middle.
Can you guys see a little louder?
So clump together in the middle.
Yeah, since we don't have anything pushing them, and like the gravity and then the link is gonna like push them, and then you will have basically just everything like in the middle. So let's see if that's right. See, it's just everything. So this is like not depending each other, just have everything and they just clamp together. And then what about the center? It's the one that keeps the. It's kind of sometimes called gravity. It's the one that keeps the node in the center of the view. So what's going to happen if I remove the center? Yeah, I'll probably have like a good layout, but it's a like flat from somewhere. So let's see. See, I mean, it's just somewhere in the corner rather than being in the center somewhere here. Sure, you can probably move everything manually, but yeah, why should we do like manual work? So actually, the collide is the thing basically. You remember I said about the sizes, node sizes. So the collide is the one that takes the node size into consideration. But I don't like the information you see because it is actually good. If you just look at it, sure, like it kind of like takes the sizes, considers the sizes, and we kind of assume that it's gonna try not to collide them and will push them apart from each other. And you can see here what happens. This is not compared to other ones, other layouts of networks. It's like not that dense. It's kind of like pushed away from each other and not like covers much area. But the data information not that good. Since it is like I don't know. I mean the nodes are actually like little tiny here, but still kind of push them apart. But I'll show another example. So and just the force xy is kind of I think it's just you give it the positions and it fixes them. So yeah, it just kind of want the nodes to be in a specific position. It's kind of you give them, and the layout tries to keep them there. It's like not guaranteed, but kind of tries to keep them there. So. Yeah, so it's now so far what we have seen is only just does the layout, but it actually doesn't render it on the screen. So obviously visualize it, you need to show it on the screen, right? So yeah, so what we do is we just say solution.nodes. So we just initialize them, we haven't done much yet. So we just give it the, remember our data, we had, it was an object, we have nodes and links. So we say, okay, the nodes are graph nodes, bar nodes. And then for the links, we say the same thing for the links. And then at the end, what it returns is it should have the XY position, right? This is what we, and the layout is essentially about the position. So everything that's returned by a layout object should have the position X, Y, or like coordinates of rectangle. So. And then here we have a detailed example that it's basically putting everything that we have discussed so far in a code example that you can go and look at it and then change parameters and see how it affects like what we have there. So I think so. Yeah, here we have a live example. So yeah, it just kind of live example of it. Yeah, you can like drag them around and then you're gonna just give you kind of some events attached, then drag it actually starts the simulation again. So if I drag it somewhere, it's gonna kind of since like tries to run the simulation again, it actually doesn't allow it to move right. So I think we have I think there are like a couple of like nice examples that kind of use customly defined forces, and So there are a couple of examples that I'm just gonna quickly show them. I think they also have the code somewhere here, so source code. Yeah. Probably have the source code somewhere down there, but yeah. So it's basically a cool examples that you can do, but again, it's kind of like since it's kind of like something custom, it takes lots of time to get it right. So like.
Takes a while to load.
So, yeah. So there are a couple of custom examples that you can take a look at to like do something custom, but they're like, yeah, we have source code, see if you can go with that. You can take them when you have time, but they're going to go with the library. So far in today is kind of like for visualizing everything, right? You can, I don't know, the pie chart, the dynamic chart, you can do a tree map, you can do a scatter plot, you can visualize a map, and like whatever you think, since it's basically manually like modifying the SVG, you can draw anything you like, right? And it's lots of like actual manual work. So I mean, even like the layouts themselves, like the kind of okay-ish, but yeah, it's kind of like lots of manual work. You even like have to create the SVG and then like special attributes and nodes. They have to append the nodes themselves as circles and then kind of position them, count them, everything. And so we have another library that I thought would be good to mention if kind of interested in my project as well. So it's called Cytoscape, and Cytoscape has two versions. It's kind of a desktop version, but we're mostly interested in the JavaScript library, JavaScript version. So Cytoscape is basically an open source library. It's only for doing graph operations and visualizing graphs. So you can't do anything else but graphs. So it's all about graphs. If you want to visualize something else, it doesn't work for it. And the good thing about this is that it comes like with lots of basically predefined graph algorithm. Let's say if you wanna run BFS, you can do it on DFS. You can do it on A star. You can do it. If you wanna like I don't know, find a path between two nodes, you can do it. So it has lots of like graph algorithms already implemented. If you want to do like something graph related, this will look cool. I mean, sure you can implement them yourself, but it takes time, right? And it also has much more like wide variety of layouts that I can kind of show you. So yeah, it's a good thing, but the thing is like, sure we have lots of tremendous stuff, but I mean there's no free lunch, so it comes at a cost. It doesn't allow you to do much modification. I mean, much customization. I mean, sure the nodes or other stuff, you have kind of predefined shapes, and sure you can affect your SVG to the background, but it doesn't allow you to do much customization. Whereas on the tree, you can do everything since it's basically just manually doing everything by hand. You can like do everything, but here it's like a thing that doesn't allow you to do much customization, but it's really good for layouts and other stuff. So here we have, I'm going to show you how simple it is compared to the tree. So here we have an example here, which basically we load the Cytoscape there, and then I also add the layout which I'm going to use. And then so there's also like a div container. It's we're going to use, I just position it there, and then I say, when I load the document, I'm just going to say, so this is like the way you define say. I'm just going to assign this the Cytoscape, and you just give it the container ID, and then that's it. You don't have to do anything else for now. But what I'm doing here, I'm just saying that okay, give my nodes some labels, and then start my edges, like append arrow shape triangle, and then just basic curves. And here I'm just predefining elements. Yeah, but then I can show you how easy it is to add them. I have like here I have like 4 nodes, and then I have like a couple of edges. So let's see what it looks like. So here I basically have like a couple of edges and nodes there, and then see, I mean you can actually kind of like most things that even like a drag drop, everything has to be down line on the tree, but here you can drag them, position them, pan them, zoom them. So you already like have most of the stuff predefined. So you actually open it there and then do some modifications. See, let's say you have nodes and okay, see, I should have my face there. Okay, it's my side script. Let's say I want to add a node. It's like as easy as this. Just say that add and then, I mean, sure, you should actually, ideally, you should define like the data or like the group and anything, but you just say add a node. Or let's say I'm gonna let's say give me the nodes. Let's give me like a list of nodes, and let's say you wanna remove them. It's gonna remove them like everything. Or let's say I want to apply a new layout. Let's say I want to randomize it. What I say is just say either, and by the way, it has a great documentation that you can go over and then lots of examples that I'm going to show you as well. So say layout, and I basically give the name of the layout. Let's say I want to randomize it. What randomize does, it's basically just a random position. It's actually just the graph is small. Actually, we get the okay layout for this one, but the bigger one actually just gets so or you can apply regular layout, or you can apply. Well, I mean, these layouts all have their like options that you can customize, but right now I'm just only giving it the name, which is the default options. Or you can say, or you can. So it's like much easier to compare to the tree, but as I said, it comes at a cost that you don't have much custom. Sure, you can like change color of node, or you can, I don't know, change shape of the simple shape is, but let's say if you want to, add an object or something in the middle of the edge, then you can put it here. So you have like, but the good thing is if it has something that we call headless mode, what it is basically just runs in the background. It doesn't have a UI rendered anywhere. Just give it the data and say, okay, just to the layout and you make the positions. And it will do it, and then you can do it and then render them in the tree. So here I have a much larger graph that I'm going to add. It's uncommon, I should add it there. Right now you cannot see it because it basically, I mean, you can predefine it, but it doesn't have any position defined, so.
That doesn't look. You gotta change the close box and then see it.
Okay, actually. Okay, cool. Actually, you can do it back there, right? I mean, if I copy it and then run in the console, I should be able to do it back. Let's see, it should work. Yeah. So I just loaded a new data set that's predefined there, and you can see since they don't have positions yet, so it just puts everything on top of each other. So let's say now I want to do a layout. I'm going to try a couple of them. This is a good one. I'm going to run that. So let's say we'll first try, what's it? I think this stands for Compound Spring Embedded, but the information that good, so yeah, I mean, you just actually basically get nothing. Well, let's say we randomize it. We'll see actually the effect of random here. It's just a mess. But by the way, I told that random is actually a good way to start the layout. Since when you start your simulation, if you don't know the position, it's still like putting everything together on top of each other. What most of the first-phase layouts do, they first do a randomization. They assign random positions and start the simulation from there, and actually they usually get much better results. So here, for example, let's say try another one. It's actually kind of okay-ish, but let's say I'm gonna run actually. I mean, basically you can see that like based on layout, it makes much more difference, right? Right now you can actually see where the clusters are, like kind of much more like it's much more like better than there's almost no link crossings or like not overlaps. But again, so this is okay. This is the same algorithm, layout algorithm, this and this, but implemented by different people. So yeah, it also makes. I think I'm also gonna go over to the website and show a couple of cool demos and then show the documentation and then we can wrap up on it. Doesn't make it that don't have it. So this is like the main side that you also have the documentation there. You can just search from there and it'll just so it's like really good documented. So I'll just look at this one. It's kind of wine and cheese pairing if you're interested and kind of thing, and you can just so you can also search from there if you want and then see, and then it's kind of like a cool demo. I thought I can dress it. So it's kind of like gives you like the cheese to pair, which you may sort of give it wine. So or we'll have it. Let's look at the different layout examples, and then we'll kind of wrap up. So you have a circle layout, which essentially basically just puts in a circle, but it might be useful in certain data types or certain graphs, but it's generally not good. But it might also kind of useful. It's kind of similar to the chord layouts, but you kind of like don't have the edges together. So, or we have concentric. We have like center circles there. Another interesting one is this one actually. This is I think it's yeah. So you have randomized here. Okay. I'm gonna run the layout. So what do you guys expect? So it's kind of I forgot what it stands for, but yeah, it's kind of good to visualize and see if you have like kind of like small groups of data in your graph, and it's kind of like good to visualize them. Here you can like kind of like put every group in a kind of second circle, and then it's kind of much more like compared to the yeah. You also have like options that you can kind of like customize if you like. Yeah, and then we have like a couple of we have a couple of force-based layouts that I'm going to show. It's basically there's like a good layout for everything. So essentially everything depends on the dataset that you have. I mean, so it basically depends on the dataset. You should choose your layout. There's like one thing that works for all the things, all datasets. I mean, if your data sets like kind of hierarchical, you might use orthogonal layouts or hierarchical layouts. But thing is, if you don't have anything else to visualize the group, then the force directed layouts is kind of like the best option to go. And then here we have a couple of them that we have the cosine that I showed you, the cosine candidate. I can also show it. And then F cosine stands for fast cosine, kind of faster version of it. And then we have Kova cosine something. And then we have like a couple of them. We also can do like animations if you like. So. But again, it's compared to the it's like much limited. We cannot you can like animatedly go from one node to another, but I mean we cannot do much customization on it. And then so we have randomize it and then see. But to be honest, the example is kind of like hand to it so that the layout. I mean, for this is a good layout in this one, but yeah, I mean they're usually. I mean, the people kind of represent layout. Pick the best one, but yeah. Randomize. So yeah, I mean, again, randomization, the round layout should get something to do with or this kind of like this is like kind of like different layout that we have Cytoscape, and then this is actually isn't that good though. Yeah. So again, I mean, at the end of the day, what you're gonna is I mean, we have lots of options in Cytoscape, not just layout options especially, but at the end of the day, the layout that you're gonna choose is basically depends on your underlying data set. So, I mean, just looking at your data, you can try a couple of them and then go on the one that fits best to your option. So, yeah, I think that's it for today. Do you guys have any questions? Yeah, sure.
Are there any tools or best practices that can help determine which layout to use based on, like, for example, the number of degrees or the number of children or some sort of generalized?
Oh, it depends on not like number of children or something. The first thing that you want to do is the data set. I mean, if you have, let's say, a hierarchical data set, then you basically you want something like a orthogonal layout or something like a layout that are like hierarchical layout category, like the ones that I just showed you, like maybe like the tree map or like a tree or an orthogonal layout. Or if you wanna let's say if you don't, if let's say you know that your data is some kind of like grid-wise, then you can use grid layout. If you know that there's like something circular, but like going into like small circle groups, then you can use a version of circle layout. But if you have that kind of run out of options, then this is when you should go to four-sided layout. But it also like depends on like the layout. I mean, there's like should be like lots of four-sided layouts, but as I showed you, just same algorithm implemented by two different people, and it just showed the result, right? It also depends on like it's basically first look at your data set, and then you just have to try to find the best one. But things actually. Cytoscape is built like one of the easiest tools to test because it's so easy to load data, and then just can do the layout. You know, get a good sense of what it's gonna look like when actually try to implement it. There's also actually other tools. There's also like Cytoscape desktop version. I think it's kind of open source as well. So you can I can still writing code. You can load your data in there. There's also another one that's a kind of conversion, but they have free version that you can test on the web, and I think it's probably like one of the best layouts that I've seen. So I think it's called Fiverr, I believe. I mean, they like you can like load your data, and they're like probably one of the like they produce really good layouts. I might actually show you a couple of examples. I think we have like some samples, so you can just plug your data in there and just try it, but don't expect the open source ones to produce. Yeah, actually some of them might do, but yeah. I think some samples over here. It's yeah. I mean, see, it's kind of like from layout you can choose layout. So it's based from there, I think. So you have like different layout options, and let's say you want circular, and then try it here. You're gonna see that it's kind of okay. But if you kind of like, you wanna like really make sense of data, obviously just doing it with like the hierarchical layout versus circular. You see if I have a hierarchical, and then go this way. So in this case, the data makes much more sense, right? It kind of like depends on the data, like data set, and then based on that, I choose an algorithm. Yeah, and it's actually a good tool if you like play with and see what kind of layouts they. I mean, they're like kind of like categories like circle, the tree one. I think the organic, it's like kind of the first one. They just give the fast name, but yeah. So yeah, it just depends on your data. Any other questions? Yeah. Okay, thanks guys. I think that's it for today.